Inertial and non-inertial frames of reference. Hey everyone, today we're going to look at what those types of frames of reference are, and free body diagrams for them, and in the idea of including fictitious forces. I'm going to start out with a little story that is at least partly true. I once had a dog named Lucky, definitely true. Lucky was a border collie lab mix, very smart, very true. One day driving to the dump, Lucky and I spent quality time together every Saturday driving to the dump, and Lucky noticed something very disturbing. This is all true so far. The recycling bin next to him inexplicably began accelerating sideways without any noticeable external unbalanced force as required by Newton's first law. Like I said, Lucky was really smart. This is where it's maybe not as true. Lucky found this quite disturbing, that these cans from the recycle bin accelerated without any force, and he jumped in my lap. That part is true. Once I explained that we were turning a corner and that the recycle bin was simply continuing in a straight line motion due to inertia that it had before the car began turning the corner. The car does have an external unbalanced force causing it to go sideways, right? Tires on the road pushing, and reaction force of the road pushing the car pushes the car sideways. After understanding all of that, that the cans were really just maintaining their straight line motion, Lucky felt much better. Obviously, that part's not true, but he did ride the rest of in my lap the rest of the way just to be safe, though. So the force that would seem to be needed to cause the recycling to accelerate sideways in the car, that I jokingly say Lucky noticed was missing, is often referred to as a fictitious force. And you'll see shortly that these fictitious forces can be included as or in real free body diagrams. All right. A lot of people think of fictitious forces as meaning that you should never actually use them or never actually work with them, and that's just not true. I'll show you. All right, so an inertial frame of reference is one in which your reference frame is not accelerating. So if you're in a car and the car is not accelerating, then you are in a regular inertial reference frame. So first and second laws of motion, they appear normal. Inertia, things that aren't in motion stay not in motion. Things that are in motion stay in motion. All those normal things, right? So all of the laws in physics, right, in fact, are obeyed identically in frames of reference that are not accelerating. So we'll see this later on in Einstein's theory of special relativity, that all laws of physics are indistinguishable in inertial between separate inertial reference frames. So if you're in a car that's going 100 kilometers per hour, or you're in a car that's at rest, or you're in a car that's going 200,000 kilometers per hour, if that was possible, the laws of physics within those cars would be identical if you had true, pristine, uniform motion, and no bumps, no jiggles. If it was perfectly smooth. Anyways, we'll get to that later. Non-inertial reference frames for today, or NERFs, as you might affectionately call them from now on. The reference frames that you're in, like the car or whatever, if they are accelerating, that's a non-inertial reference frame. So in that scenario, the first and second laws of motion do not appear to be obeyed, right? And they aren't obeyed as viewed from that non-inertial reference frame. So in order to fully describe motion in a non-inertial reference frame, you either need to consider the accelerated motion of the reference frame, or you can draw in fictitious forces, right, to explain the motion within that non-inertial reference frame. And quite often that's a pretty handy thing to do. All right. So, for example, in a car slowing down, you notice an apple accelerates forward at 3 meters per second squared and falls onto the floor without anything touching it to cause acceleration. Question is, what force caused the apple to accelerate at 3 meters per second squared relative to you in the car? Well, the answer is there's no force at all. The apple was really just traveling at a constant rate. The car was actually slowing down, right? So you can even calculate the value of that fictitious force, the acceleration times the mass. You get this like 0.6 Newton fictitious force, right? So we know that it doesn't actually exist. We know it doesn't actually exist. This is kind of weird wording here, but it does make sense to. I'm going to reword this here. So even though it doesn't exist, I suppose, right? So even though it doesn't exist, in reality, it can still be useful within that non-inertial reference frame. So even though it doesn't actually exist, it is useful to use, or it can be used in the non-inertial reference frame to analyze motion. I'm trying to remember how we spell that, Canada versus the States. I think we use a Z, right? Analyze. Oof. There we go, missing an L. Analyze motion in non-inertial reference frames. All right, that's what I'll stick with. So here we go. If we're looking at a free body diagram for that apple that appears to move and accelerate forward, the free body diagram relative to the Earth is really this, right? You just have the force of gravity and the normal force holding it up, right? There isn't a force, right? It's just maintaining constant velocity relative to the Earth. In that non-inertial reference frame, though, you can draw it as having this 0.6 Newton perceived or fictitious force, right? So it actually does make sense to include that fictitious force in that non-inertial reference frame. So in a case like this, if you had an object hanging in a car and the car has acceleration, and as a result of the acceleration of the car, the object is hanging like instead of hanging straight down, it's angled back at 10 degrees, then we can look at free body diagrams for this, right? So in the inertial reference frame, you'd have the force of gravity and the force of tension. We'd have a x component of that force of tension. The y direction stuff would balance out, of course, from our equilibrium force material, right? Since the acceleration in the y direction is zero, the net force in the y direction is zero, and it would lead to that normal stuff. In the x direction, though, there is a net force and there is an acceleration, right? So instead, it kind of looks like it's being pushed backwards, right? Well, in that non-inertial reference frame, you can explain the zero acceleration relative to the car very effectively by saying, okay, well, there's this applied force backwards, that fictitious force backwards. So we could call that force like the anti-acceleration force or the resistive force or whatever. And then in circular motion, you're going to see in the next lesson, that's exactly what people do. They call it a centrifugal force. All right, so it's good to sort of talk about the idea of this force here, that really, because it'll really help us understand circular motion. Yeah, so that normal stuff there, and again, this is logical as a free body diagram in a non-inertial reference frame. Right, that's absolutely what we're going to do in circular motion. So to determine the angle, the acceleration based on the angle, we could actually calculate based on this. We could calculate the acceleration of the car. Kind of a neat thing, right? Using some of our Newton's laws and analysis abilities here. So we know the acceleration in the y direction is zero, and so the net force is zero in that y direction, and so on. So we have this tension force y component is equal to the gravity force, right? That's probably just my free body diagram. And then you have some things here. So we can get the tension force would be just the cosine of the 10 degrees times that tension force. So tension force in the y direction is Ft cos 10. We have the force of gravity is m times that negative 9.8. Now notice that the gravity force is down, and then we're subtracting that to the side. So we are getting a correct double negative situation going on here. And so we end up with the tension force being m times 9.8 divided by cos of 10. And so in this case, there's I guess we're going to have two unknowns soon here, right? So the tension force is this 9.95 m, right? The amount of tension force depends on the mass, right? The amount of tension force depends on the mass, but does the acceleration. So with this, if you look at the net force in the x direction, then we have m times the acceleration in the x direction, the mass times that, and we know that's the x component, so the ft sine 10, right? So when we combine those, basically we're doing substitution here, right? We're putting in the tension force, and so we end up with the masses canceling out. So it gives us the acceleration. It's just going to be 9.95 times sine of 10. Yeah. Oh, I lost my, no, I didn't. I thought I lost my cos 10, but I didn't because I divided it out. Often I would leave that cos 10 there, end up with a sine 10 over cos 10, and then remind you that that can be calculated as tan of 10, right? So yeah, so there's your calculation example there for getting the acceleration of a system, of a reference frame, based on how a pendulum or something hanging on a string is deflected backwards, right? You don't even actually need the mass. If we had the mass, we would have felt good about things. We would have calculated and got a force, and then here we would have just had the component of that force, and we would use the mass here, and it would have seemed like everything's fine. We can use a mass, but you don't need the mass. So it's good to recognize when you don't need a mass. So there's just a recap of our inertial, non-inertial reference frames. So another non-inertial reference frame situation, other than like a car accelerating sideways, things like that, would be with an elevator. Okay, and with an elevator, we often end up talking about apparent weight. Okay, so if you're in an elevator and it quickly goes up or down, you feel like heavier or lighter for an instant, right? In fact, if you accelerated down at 9.8, you would have no normal force on you at all. You'd feel weightless, right? You wouldn't have any force needed to hold you up. You'd be floating. And so apparent weight is what you're feeling in that scenario. And so the try this, grab a bathroom scale and stand on it, and then quickly go into like a squat, like squat down really quickly, and you'll see your weight reduces. And then if you quickly stand up, then you'll see that your weight on the scale would increase, right? So the apparent weight kind of calculations we're looking at, right? As you lower yourself and so on, we know what I just talked about here, right? So this first part here, just says just calculate what the reading on the scale would be if the elevator is not moving. Well, obviously that's just complete review. That's just Fg equals mg, right? So um, we have this acceleration to 0 in the y direction. To be more thorough about it, though, so we end up with the gravity force, just our normal force equals the opposite of the gravity force, and so we have this negative of the negative business here, right? So they end up with showing it as negative down because gravity was in as down, and so on. Did they put they put as a direction system here up as positive or negative? I don't know, whatever. It's fine. So not worth analyzing too much because it's review, right? I want to just stick to the new stuff here. So now if we have the elevator accelerating upwards, then that's, going to change things here, right? We're going to have an acceleration upwards. So we don't have a net force of 0 anymore. We have a net force of ma, right? So we're going to let the upwards direction be positive because that's the way we're accelerating. And we have F net equals ma, and we also have F net equals the sum of all the forces, right? And so if we put them together, we have first of all we have the F net equals ma stuff, right? So F net equals ma is 50, and then so the 50 is going in as the net force. So we have the normal force plus the gravity force equals 50, and so then we have, when we solve for Fn, we can subtract the gravity from each side, right? So that when we subtract that gravity, notice we're subtracting a negative, right? And so really we're adding that force on. My preference would have been to have the numbers just plugged in. Where do I want to start? Right here, I guess, right? So we'd have the normal force and we'd have the gravity force in as the negative 50, and we'd have the net force of the 50 or sorry, what was the gravity force? 490, not 50. So negative 490.5. And then we just add that to both sides and so on, right? So add that number to both sides and end up with this, obviously here, the 591 up. Point being there, that the normal force is increased by that analysis, right? And so paraphrase here in the end, therefore, blah, blah, blah. And what if the standing elevator scale would read the elevator begins to accelerate upwards at the, oh, this is just this solution, or the difference here. by just analyzing further, I guess here, but there's really an additional 50 Newton force up on the person, but it would feel like you're being pushed down by an imaginary force, right? So this is our free body diagrams for these things. So with the acceleration in the y direction being 0, we of course just have normal stuff like that, and then with the acceleration up, right, you have this extra 541 that we calculated out. You have this increased normal force, but in the non-inertial reference frame, you can picture it as this, right, where you have these two adding together, right? So in order for this scenario here to lead to an acceleration of 0 relative to the elevator, there must be this additional force downward, right? And that's that kind of fictitious force here, right? So in reality, we know, of course, in the inertial reference frame, it's accelerating upwards, right? So you have two scenarios. You have, the accelerating upwards version right here, right? And then you have the non-inertial reference frame version. So that as it stands right now is the non-inertial reference frame version, right? And then you just look at just this part right here, right? That's the inertial reference frame. In other words, the blue one acknowledges that you're accelerating upwards, whereas the red one is like, okay, well, you're at rest. You're not accelerating either relative to the elevator. And so you must have a net force of 0, right? So you'd have to include a fictitious force to have that net force of 0. So these guys here, what if you're, what would the reading on the scale be if you're maintaining a constant upwards velocity or downward velocity? And what would reading on the scale be if you're still going up and then the acceleration starts to slow down, right? So we have an acceleration in the negative direction, right? So part C is easier than you'd maybe think if you're not noticing the difference, right? But the simplest answer would just be to say that, constant velocity is the same as 0 acceleration, and so it's the exact same as the work we did in part A. And honestly, that's the same stuff as part A essentially, right? You can look through the file and whatnot later on, like, or pause the video or whatever, but it's the exact same stuff. So I'll just show it there again. In D, then now we have the acceleration is in the negative direction, right? So we have net force, and we're letting, what did they do here? They let down be the direction of acceleration. Let down be the direction of acceleration. So let down be positive. Just watch for that in the analysis of things, right? But in which case gravity is going in as a positive number and so on. Long story short, that math works out to giving you a reduced normal force, right? By normal work that usual work that we've done. So at this stage here, we just would have that normal force that we want to know, and we'd have the gravity in. Now they said let down be positive, right? So that's going to go in as a positive 490.5, and then we have this net force down. Just make sure I get my bearing straight here. The F net equals this number here, the 50, right? So it's 50 as well. And so we're subtracting from both sides, and we end up with this, negative 490 number. So negative 490 down, in other words, right, that we get from this. Right, so that's going to lead to this. And yeah, so obviously that means up. The normal force is smaller and up. Whether you choose to have the direction down be positive or not, it's up to you. You can obviously do this work with the other direction system. And this section here, I want to show this video here. Hopefully I don't get I'll have to edit it out if I get a copyright strike here. I'll go to where is it? I'm having trouble finding it here. Oh, it must be on this one. There we go. So super old video, but super good actually. Like it's impressive what they were able to do back then. And it'd be so much easier to make a video like this now, of course, right? But there we go.
We're used to seeing things from a particular point of view. That is, from a particular frame of reference. And things look different to us under different circumstances. At the moment, things look... You look peculiar. You're upside down. No, you're the one that's upside down. No, you're upside down. No, I'm not. He's the one that's upside down, isn't he? Well, let's toss for it, all right? Okay. You lose. He's the one that's really upside down. You better come into my frame of reference now. All right. My frame of reference was inverted from what it usually is. That view of things would be normal for me.
Oops.
Me if I normally walked on my hands.
So obviously it's all about the idea of different reference frames and that, what you'd observe in different reference frames. And so right now, let's let it play here.
You see the...
Sorry. Oh boy. I was thinking there's more of a gap in between here.
My frame of reference was inverted from what it usually is. That view of things would be normal for me if I normally walked on my hands. This represents a frame of reference, just 3 rods stuck together so that each is at right angles to the other 2. Now I'm going to move in this direction. You see the frame at the same spot on your screen, but you know I'm moving this way because you see the wall moving this way behind me. But how do you know that I'm not standing still and the wall moving? It was the wall that was moving. Now the wall has disappeared, and you have no way of telling whether I am moving or not. But now you know that I'm moving. The point of this is that all motion is relative.
So the internet's not working great here today, so I'm just going to skip that. But please watch the video. Just put it on, fast forward, put it on 1.5 or something like that. You got some pretty good stuff in there. So it's, I don't know, it's worth a watch. So I'm not even sure if sound was working for you or not. So there we go. Yeah. So practice questions, do with it. You got the school bus stopping or going along, driving along with constant velocity, the optional ones here, you don't need to submit those as it clearly says. So just the 3 questions you're submitting. Alrighty, so there we go. Thanks.